Alright, what's up, team? I'm here. We're going to be doing the parallel problems section of the review now. Let's do this first one with all three versions of the test. This is actually a conceptual question, but this is exactly the same as it is on the test. Remember, all these questions are exactly the same as they appear on the test. The only difference is the numbers that I chose. So this question is going to be exactly the same. This 16 will be a different number. That's the only difference. Right? So I want you to think about this first one conceptually. This is a multiple choice question, by the way. A, B, C, D, and E here are not parts. I know that a lot of my questions look like they're parts. That's my bad on like my formatting or whatever. But this is a conceptual question. So I want you to think about it. We have a package dropped from an air balloon 2 times. In the first trial, the distance between the balloon and the surface is x, and the second trial 16x. So that means the second trial takes 16 times is 16 times higher. It's 16 times higher off the ground. I want to compare the time it takes for the package to reach the surface in the second trial and the first trial. Okay, so here we have an object that's accelerating. It's accelerating based on free fall, right? So because this is accelerating, and because it equals, because it's accelerating and because this equals distance, we're finding distance, right? We can logically think about this, first of all, as a much higher height. Obviously, it's going to take longer to hit the ground, right? If I raise the height to 16 times higher, it's going to take longer for it to hit the ground. Obviously, I'm dropping from higher up. So we want to see exactly what effect that'll have on the time, though. And you may want to say that it will be 16 times as long because it's 16 times as high. Logically, you're thinking that kind of makes sense 1-to-1. But here's the thing, though. Distance and acceleration have an interesting relationship, because acceleration is a change in velocity over a change in time, whereas velocity is a change in distance over a change in time. Which means that acceleration isn't a change in distance over time, it's a change in the change in distance over time. Right? Acceleration is saying the thing that affects my distance traveled is changing for as long as the thing is accelerating. It's a change in distance over time, which means that actually acceleration is based on a factor of t squared. We can think about this if we think about our fourth kinematic equation, right? We have delta x equals vi times t plus 1/2 a t squared. Do you see how this t here is squared? This a depends on a t squared, because as acceleration increases, it's also increasing velocity, right? As this object is accelerating, its velocity is increasing. Not only is its position increasing from its previous velocity, but it's gaining velocity too. So that means that time is going to exponentially increase here, right? It's based on this factor of squared. So these are dropped from rest, right? So that means that our vi is 0. This part's going to drop out. And we can say that delta x equals 1/2 at squared. So if I multiply this side by 16, my factor of t, because this t is squared, is going to change by the square root of 16, which is 4. So the time in the trial is going to be 4 times greater, because this t is squared. Hopefully that makes sense. And again, this is because as the thing is accelerating, it's gaining velocity. The rate at which it's gaining ground is also changing as it speeds up. So because of that, it will take 4 times longer for 16 times higher. It's the square root of this, the square root of the amount. This question is kind of hard to wrap your head around. That's why I put it on the review exactly. This is going to be an even square on the test too. So it's not going to be like 23.1. It's going to be a number that comes out evenly in a square root. So that's how we do that first one. See you next time.